As of the 2020 National Electrical Code, conduit is required to carry a separate grounding wire inside the conduit instead of relying on the conduit itself as the grounding path. The primary reason for this change is that conduit is no longer considered a consistently reliable path for grounding. Several factors can affect the conductivity and integrity of a conduit system over time. These factors include corrosion, loose connections at couplings and fittings, and physical damage to the conduit. Any of these issues can increase the impedance of the grounding path, which can compromise its effectiveness in clearing ground faults. When a ground fault occurs, a large amount of current flows through the grounding path back to the source. A low impedance grounding path is essential to ensure that this fault current is high enough to quickly trip a circuit breaker or fuse, thus disconnecting the faulty circuit and preventing electrical shock or fire hazards. If the impedance of the conduit grounding path is too high, a fault current may be limited, which can delay or prevent the overcurrent protective device from operating. This can create a dangerous situation where exposed metal parts of electrical equipment become energized, posing a risk of electric shock to anyone who comes into contact with them. The separate grounding wire, also known as an equipment grounding conductor, provides a dedicated low impedance path for fault current to flow. This ensures that the overcurrent protective device will operate quickly and reliably in the event of a ground fault. The size of the equipment grounding conductor is determined by NEC Table 250.122, which specifies the minimum size of the grounding conductor based on the size of the overcurrent protective device protecting the circuit. It is important to note that the equipment grounding conductor must be installed in the same race rate or cable as the circuit conductors. This helps to minimize the impedance of the grounding path by reducing the inductive reactance. Inductive reactance is a phenomenon that occurs when alternating current flows through a conductor. It is proportional to the frequency of the current and the inductance of the circuit. When the circuit conductors and the grounding conductor are separated, the inductance of the grounding path increases, which increases the inductive reactance. This increased inductive reactance can impede the flow of fault current and reduce the effectiveness of the grounding system. By installing the equipment grounding conductor in the same raceway or cable as the circuit conductors, the magnetic fields produced by the conductors tend to cancel each other out, which reduces the inductance and inductive reactance of the grounding path. This ensures that the grounding system will operate effectively in the event of a ground fault. There are several types of equipment grounding conductors that are permitted by the NEC. These include copper conductors, aluminum conductors, and copper-clad aluminum conductors. The type of conductor used must be suitable for the application and must be protected from physical damage. In addition to the equipment grounding conductor, the NEC also requires that metal enclosures and equipment be bonded together to form a continuous electrical path. Bonding is the process of connecting metal parts together to ensure that they are all at the same electrical potential. This helps to minimize the risk of electric shock by preventing voltage differences from developing between different metal parts. Bonding is typically accomplished by using bonding jumpers, which are short lengths of conductor that are used to connect metal parts together. The size of the bonding jumpers is determined by NEC section 250.102. It is important to ensure that all bonding connections are tight and secure to provide a low impedance path for fault current to flow. The requirements for grounding and bonding can be complex, and it is important to consult the NEC and other relevant standards to ensure that electrical installations are safe and compliant. It is also important to use qualified and experienced electricians for all electrical work. The dedicated equipment grounding conductor provides a reliable low impedance path for fault current, ensuring that overcurrent protection devices operate quickly and safely. This change in the NEC emphasizes the importance of a robust and reliable grounding system for electrical safety. Properly sized and installed grounding conductors, along with proper bonding techniques, are essential components of a safe electrical installation. The NEC provides detailed requirements for grounding and bonding, and it's crucial to adhere to these standards to minimize the risk of electrical hazards. Understanding the reasons behind the code changes, such as the decreased reliance on conduit as a grounding path due to potential corrosion or loose connections, highlights the importance of continuous learning and adaptation in the electrical field. Staying updated with the latest NEC revisions and best practices is vital for all electricians and electrical professionals to ensure the safety and reliability of electrical systems. Factors such as proper selection of grounding conductors based on circuit size, as defined in NEC Table 250.122, and ensuring they are installed within the same raceway as the circuit conductors to minimize impedance are crucial considerations. Bonding metal enclosures and equipment together to create an equipotential plane further enhances safety by reducing the potential for voltage differences and shock hazards. The use of appropriate bonding jumpers, sized according to NEC Section 250.102, and ensuring tight and secure connections are also essential aspects of a well-designed and installed grounding system. By understanding and implementing these requirements, electrical professionals can contribute to creating safer electrical environments for everyone. The 2020 NEC mandate for separate grounding conductors within conduit signifies a shift towards prioritizing dedicated grounding paths. This change reflects a recognition that relying solely on conduit for grounding can be problematic due to factors affecting its conductivity over time. The use of a separate equipment grounding conductor ensures a consistent and reliable low impedance path for fault current. This dedicated path facilitates the rapid tripping of overcurrent protection devices, such as circuit breakers or fuses, in the event of a ground fault. The result is a significantly reduced risk of electrical shock and fire hazards. The grounding conductor's size is determined by the rating of the overcurrent protective device protecting the circuit, as specified in NEC Table 250.122. This ensures that the grounding conductor can safely carry the anticipated fault current. Moreover, the NEC stipulates that the equipment grounding conductor must be installed within the same raceway or cable as the circuit conductors. This proximity minimizes impedance, which is crucial for efficient fault current flow. Inductive reactance, which can impede fault current flow, is reduced by this close proximity, as the magnetic fields of the circuit conductors and grounding conductor tend to cancel each other out. Various types of conductors, including copper, aluminum, and copper-clad aluminum, are permitted for equipment grounding conductors, provided they are suitable for the application and adequately protected from physical damage. In addition to equipment grounding conductors, bonding plays a crucial role in ensuring electrical safety. Bonding involves connecting metal enclosures and equipment to create a continuous electrical path, bringing them to the same electrical potential. This eliminates voltage differences between metal parts, minimizing the risk of electric shock. Bonding jumpers, sized according to NEC Section 250.102, are used to connect these metal parts. Ensuring that all bonding connections are tight and secure is essential for maintaining a low impedance path for fault current. Compliance with NEC requirements for grounding and bonding is essential for ensuring the safety and reliability of electrical installations. Consulting the NEC and other relevant standards is crucial for understanding and implementing these requirements correctly. Employing qualified and experienced electricians for all electrical work is also vital. The NEC updated requirements for grounding and bonding reflect continuous effort to enhance electrical safety. By adopting these changes and adhering to best practices, electrical professionals can significantly reduce the risk of electrical hazards and create safer electrical environments for everyone. The reason behind the shift is that conduit connections can loosen over time, or rust can build up and compromise the ground. Therefore, a dedicated ground wire is needed. This wire, which is sized based on the circuit's overcurrent protection, provides a reliable low impedance path for fault current to return to the source. This ensures a fast trip of the breaker or fuse. The NEC mandates the ground wire be run in the same conduit as the circuit conductors, minimizing impedance. Remember to consult NEC Table 250.122 for proper sizing and local amendments, and always hire a licensed electrician. Firstly, a dedicated grounding wire ensures a reliable, low impedance path for fault current, even if conduit connections become loose or corroded. Secondly, the ground wire size is determined by the circuit's overcurrent protection, as detailed in NEC Table 250.122, guaranteeing it can handle the anticipated fault current. Thirdly, running the ground wire within the same conduit as the circuit conductors minimizes impedance, crucial for swift response from overcurrent protection devices. One must consider that electrical codes are updated regularly, and local amendments may exist, so always consult the latest version of the NEC and local regulations. Two important aspects of electrical safety include proper grounding and bonding techniques, which are essential for minimizing electrical hazards. 3. Engaging a licensed electrician ensures compliance with these complex requirements and the safe execution of electrical work.